talk a bit about Rebol internals, both historical Rebol internals around the time of when Carl had open sourced R3 Alpha, and then some of the cool changes. And sometimes when looking over some of this bit fiddling, I'm sure that people might think that it's over the top. And Paul Graham in the 100-Year Language was talking about like someone who grew up poor and can't bear to spend money even for something important like going to the doctor. And maybe some of these bit fiddly decisions are going to seem like that. It may not be whether it's important or not. One thing I just want to cover just to understand about Rebol, it looks kind of lispy. You're looking at these blocks of things and you might think, is that a linked list? The car and the cooter of Lisp. No, they are arrays of things that are called reb-vals. They were chosen to be 4 platform pointers in size. And that was a choice that Carl made that we've continued. Haven't made them any bigger. Some things are going to make sense to you here, like a Unicode character or a what's called a SRI, a series and an index. So that's 2 things. When you look at a block like that has several values in it, that block is 4 cells long, and the 4th cell is a terminator. If you're just going to churn through a block, your pointer is marching along in memory, and then you just look for a cell flavor that is an end. And Ren-C has enhanced this, and I'll explain some of that. There were some alignment issues initially, especially in the 64-bit build, where things like a double wants to be on 64-bit boundaries. When that wasn't done right, the Inscript and JavaScript build, because of a pragma, which is non-standard, and it was misaligned. And the weirder your C platform is that you're compiling to, like the more alien it is, the more likely some of these things are going to be problems. So that's when you have to respect the standard, because these alien platforms, they follow that standard to implement it. The cells being this size, everything works out as a good power of 2. We find that this is something that was chosen on purpose and is a good concept. Now, obviously, values that have varying sizes, like strings or other blocks, you can't fit an arbitrary amount of data in 4 platform pointers. So that series index, these fields that were inside that value cell, that rebsir, it just points out to what we might call a series node. It had a pointer to the data. It had a count of how many items were in use, which it called the tail, because that's the index that got you to the tail. It had something called the res, which is the total allocated capacity. It had some flags. It also stored the size of images, because images were actually also the same data type. And so these things come out of pooled memory. Something that has changed in Ren-C that's pretty foundational is that we do not decode UTF-8 strings into fixed size code points. Strings are kept as UTF-8 the whole time and only transformed, like only on Windows and only when you're inputting or outputting. So that means the Linux build doesn't have any UCS2 or UTF-16 or anything. We support all the code points. We support the emoji. I think that when you look at the trends of where software is going, carving out all that junk and worrying about whether you're widening the string or narrowing it, it is something that's rare and unusual. The only other language I know that does this is Rust. Okay, so I'm going to go straight to the point, which is about how UTF-8 is used to discern a UTF-8 string from a cell or a series. The way UTF-8 works, there are some bytes that can never begin a UTF-8 code point sequence. So if you're at the beginning of a string, you would never see a UTF-8 string that began with the leading bits 1, 0. Those are only continuation bytes. And since that can't begin an encoded code point, they also can't begin a UTF-8 string. And there are a couple of bytes that can't appear in UTF-8 at all, CO and C1, as well as any bytes greater than F6. So the concept that I had was to twist the format of the underlying binary C structures such that their first byte cannot be confused with the first byte of a UTF-8 string. Then an API could pass a mix of string pointers and Rebol value or instruction pointers on the stack, which could be sniffed and discerned at runtime. So this idea was to rethink the anatomy of a cell a bit, such that the header actually, no matter what your platform you're on, big endian, little endian, it will lay out a very specific pattern for the byte orderings. And we actually do access it by byte. So we're not masking an integer. We're actually, and this gives us also the advantage of beating something called strict aliasing. The char data type of a single byte is not subject to the rules of strict aliasing, which means that we can actually have these different data types that are coming in as a void pointer, and we can look at that first byte and discern it. So here we see the anatomy of a cell, and we see that's the 1, 0, and then we have some other service bits that are used for other purposes, and it ends in a 1. We then have something called the extra, which has to be it's a disjoint field for certain reasons, but one reason is that pushes the alignment of the payload onto a 2 platform pointer boundary. So on a 32-bit system, we're actually pushing that alignment to do the doubles and stuff into that payload region, which was, as I said, an issue that we had with R3 alpha, and we were trying to do some other stuff. And there's some mechanical reasons why this extra, which holds, among other things, bindings, and that binding field is read generically out of cells that have had different assignments. And you can't, once you disengage a union, you assign it through one union, you're never supposed to read it back through one of the other union fields. So the extra is actually broken out instead of combining the extra with the payload, which would cause problems with that. The second byte here is always a cell kind, like a reb block or a reb integer. And there's this been restricted down to specifically just 64, counting 0 for end. Because now, if you have a user-defined type cell, it sacrifices the extra to point to its actual type. So then that's how we now have more than just a fixed number of cell types, but what you get is that user-defined type only has a payload available in its cell format. It has to give up this extra. But the built-in cell types have the extra for other work. There's something called the mirror byte, and that is in order to have cells, they can hold things but pretend to be something else. There's no refinement in Ren-C, for instance. So it's a path that can have a word in it, but that means its kind is a path. But the mirror byte, if the mirror byte is different and it says it's a word, that's how you know you have a refinement. And then more cell flags. These are used all kinds of ways. Skipping on, all right. The first byte is not contentious with the first byte of a valid UTF-8 string, starts with 1, 0. The lowest bit indicates whether the header represents a cell or a node. And that reason is because the second bit is used to mark items being free. Now, that will make them start with 1, 1, and that's actually a valid leading UTF-8 byte format, but it's free. You're never supposed to be having these free pointers, so it's just we use that as a signal. In valid code, you should never be receiving a cell or a series that starts with 1, 1. Interestingly, the 0 byte terminator, we don't have to have a whole cell. We only have to have that second byte be 0 in order to consider it a termination. So even though we often do have an entire cell's worth, like if we had allocated a series node, then we can do that. But we can also signal an end, for instance, very trickily, with just a 2-byte C string. Now, what do we know about C strings? They're always 0 terminated, which means that all you need is a 1-character string with a little signal here, and just a byte, and then a 0 byte, And you can just type that in C as a quoted string with one character in it. And that can signal an end of a enumeration for input. So we can do this other places too. So the nodes are now a bit larger. We saw before they were 5 platform pointers large. And what we're looking at here is something that's 8 platform pointers large. So this is vertical. Count vertically for the 8 platform pointers. But among things we can do is, because now it's 8 platform pointers long, in the middle on a 64-bit alignment point on a 32-bit platform, we have room to put a 4 platform pointer cell if we need to. If you have a single length array, it's terminated by this 0 byte. And 0 is used to indicate that this node is actually of the array type. So if you want to know that something's for a block or a group, the signal for that you check, there's no other bit used anywhere else, the signal for that is 0, which then gives us that advantage that array is terminated, does double duty. And then we have our information flags. If we have a small series, like a short string, again, we don't need a separate allocation. And also, because we're using UTF-8 everywhere, words and small strings can all fit here inside the series node. But if you have something that's larger than that needs an actual allocation, then you're going to break down this this middle part, the content, into tracking information. So you get the data pointer, you get how much of the information is used, what Carl called a tail, you get the rest, and you get a bias, which is how far off of the head of the data you are. So Carl did something, and we've kept it in Ren-C, which is that if you take away things off of the head of an array or a string or whatever, it actually bumps the data pointer. So it's no longer the pointer that was allocated by the memory allocator. It moves it, which means that you don't have to add in, you can get to the start of the data directly. It means you have to back out that bias in order to free it, otherwise you're giving it an invalid pointer. So you'll see a couple of other fields here that we have available, the link and the misc. Depending on what kind of thing you're looking at, what kind of series node this was for, you saw that in the R3 alpha, it actually had like the size of an image that it tried to pack into an extra field here. So we still, we don't still do that, because actually images are now a custom data type loaded by an extension, which means that it allocates like a 2-element array, one element of which is a pair, to track the information. But yeah, this is pretty well mapped out and commented in the source, so you can kind of see how these decisions have come together. And we also have one other option that we can do, which is we can put two cells, like a pair, for instance, of values into this same pool, because we make it very fast to allocate these 8 platform pointer items. And I mentioned this UTF-8 thing because that is how, when we have this pretty slick, easy to use API for calling into Rebol and being able to mix up values in a Variadic style with segments of string material. So we actually run through the scanner, and when the scanner hits, the scanner takes a CVA list, and as it's processing the CVA list, it can process a string part, and if it hits a, something that it looks at, in this case, this says reb_i, that's a way that in the C it makes an integer that uses the series node format. It just allocates that, but then it knows it can free it as soon as it visits it. So while it's walking along here, it will free that. So it considers these to be instructions. So it's using a series node. And then we have another segment of what's recognized as UTF-8. We can tell from that first byte. And then here we have what's going to be a value cell. In this case, it's a function that we got. And it can tell that that's a value cell. And then we can end. So you can span segments of the code which open a brace or open a bracket in various locations. And we're able also, I pointed out that C, you can just have that one character C string to signal a terminator. We actually, you have to put that explicitly in C89 because C89 VA lists and C99 VA lists, they don't tell you how many things are there. So you always have to either have, like in printf, it knows how many things there are because it knows how many percents you used. And then, but here what we would have to do is you would have to put an end signal. But we use a trick, which is that in C99 has Variadic macros. So we just have a wrapper over an implementation of a function like reb_value or reb_elide. And what that does is it just tacks it on the end. So if you're willing to use C99, then you don't have to put a reb end on the end of your Variadics, which is nice. And of course, the TCC compiler can do those Variadic macros, which means that in user natives, you don't have to terminate it. That's a major talking point for the API, but that's kind of all I'm going to say about it so that I can move through some more details about things that have changed since R3 alpha. Feature-wise, I mentioned UTF-8 Everywhere and the fact that we now use UTF-8 for both strings and words. R3 alpha, to save on space, and because words were immutable, would use UTF-8. But it would go ahead for strings and to cut them out. Well, one advantage that we have from having them in the same format is now you can alias them back and forth. So you can alias a cell that's holding a word as a read-only string. Comparisons are faster. But because we're putting them in series nodes, just like everything else, just ones that have been marked read-only, we have GC for words. And we still, for series nodes, I didn't point it out, but there's enough space that if you have a word series node, it has a symbol number for any of our fixed words that the system knows about. So we can still do switch statements that are picking based on numbers of the symbol number, which is, that helps speed up things like parse or whatever. So you're not always comparing pointers. R3 alpha and Red both, I believe, work with a data stack. In R3 alpha, it would basically force you each time you went to push to the stack. If you weren't confident that there was enough space, you would have to treat it like any other series and say, hey, is it big enough? And if not, you'd have to reallocate it. In order just to make it easier to write natives, there was an assumption of, well, each function call that you do it had to just bump the count by 20 so that you weren't in every native having to worry about how much stack space you had, as long as you only used a little bit. That put a lot of pressure on those routines that suddenly are using more stack space, something like a compose or a reduce, because what they do is they don't know in advance how long the thing they're going to produce is. Instead of trying to allocate and then reallocate, they will push to the stack to get an accurate count and then create an array exactly that long and then put the stuff into it. And that's not necessarily always the best idea, but it was how it was done, and it's fine. In Ren-C, we do things differently. Each time the data stack gets expanded, it fills the unused capacity of the stack memory with things that are not end markers. And then it sets the last cell in the data stack to an end marker, which means that all a push has to do is to check the next top of stack for an end. If the cell it's about to push into, the memory that it's interested in, most likely, if that is an end, then it knows it needs to do a stack expansion. And then when it pops the stack, we don't ever allow you to push an end to the stack. So popping doesn't really have to do anything other than move the stack pointer. That means that we have all the benefits and the locality without having to have this arbitrary bumping of the stack by 20, and yet each stack push site can just run pretty simple code. This is probably out of date code, but still relevant. Let's talk about a problem that was in R3 alpha. Carl didn't want to move memory around too much. If he could avoid it, he would have something maybe return from a function and know that it was supposed to get the result from the top of the stack. So things wanted the stack to balance, so they would pop things, but then they would tell the code, oh, it's still there. So it balanced the stack, but it kind of lied. It used to be kind of confusing. You'd have the warning like, oh, by the way, this pointer is going bad, and could be wrong. So we don't do that. Instead, when the evaluator is recursing, it doesn't have to copy values anywhere. It actually has a fixed location, a pointer that doesn't move during the entire function call, that is an out parameter, which is like a complement to the arg or ref macros if you read R3 alpha source. The GC knows about it. It protects that fixed location. And yeah, we don't really use the data stack unless we're doing something stack-like. What this means is that you can start off at the top of an evaluation, pass in that pointer, and then the next guy can say, oh, I want to write there too. And then it goes, oh, I want to write there too. And so instead of less copying, you often get no copying. So that means that the stack is balanced evenly on every evaluation. The debug builds are good in terms of wiping out pop cells of trash, so we have a lot more control. Stack bugs are very rare. There was kind of a strange thing I've learned about early on, which was that the GC saw all series that were allocated, looks at all the cells, sees which ones have series references in them, and if it does, it just marks them through the transitive closure. So that means that maybe you just made a series, but you're not ready to put it in a value yet, or something. These were called the GC infants. And there's a constant, like, how many series should it be saving? And it kind of said, the last 5 series, they're in our working set. Maybe just go ahead and mark those because they might be in use and just didn't make it into a cell yet. And that wasn't a very good idea, but Carl knew that. And he wrote about it, saying, oh, here's something we need to do. And it's pretty much been done. When you create a series, it's tracked manually by default. You can pass in a flag that kind of is slipstreamed into the series at creation time, so you don't have to doubly initialize the header to say, hey, I know I want this to be managed. But if you don't do that, then the series will stay protected as a manually allocated series until you free it. If you ever migrate a series into being managed, then free series is you shouldn't call that on it. But yeah. So, and for now, created series must either be moved to a freed or managed state at the end of every evaluation. This is a technical problem that it used to be that when you call the function, and it would just push its arguments to the stack, just like it was pushing cells to the stack in order to do a compose or to do a reduce. Each function call would just push some stuff onto the stack, and so each function knew which index each parameter lived at. But what that meant was that if the stack got resized, any pointers that you had cached or stored to those arguments would now be invalid. And there was a warning that said, do not cache pointers to stack args, the stack may expand. But this was broken like everywhere. Even in pretty basic code like here, reduce, back when arguments were referred to by numbers, we now have a little set of macros that gets injected at the top of the function, so we can get the numbers, but we get them by name inside the natives. But if you look at what this is doing, it's calling into reduce, which is calling into evaluation, and it's using cache pointers. So if the stack expands while you're doing this reduce, then you can come back up, or these various pointers can go bad, which can confuse whoever you've called. So it's fixed, and there was once a diagram of it, but we don't have that anymore. But there are comments in the code. So a lot of combining iteration and mutation would kind of throw R3 alpha out of whack. This was a pretty basic example which was found, that if you're parsing and you clear the rule while you're parsing it, you have a problem. You would have this kind of problem if you were doing it, during an evaluation, if you run a do. And you didn't usually notice it crashing because even if, when you clear a rule, it wouldn't actually generally free or reclaim the memory. You're just kind of stepping outside of the bounds of your array. So several places in Ren-C have been changed to pretty much temporarily take holds on things that are either being parsed or that are being evaluated. And that also lets you be more efficient, because otherwise you go to do something and you don't know if the length's changed, you don't know if your pointer's still good. So you're always checking the updated length. And to me, it's just kind of like you're getting nonsense behavior. The semantics would be bad anyway. So having a sort of a systemic concept of having holds is useful. So that applies to many things. Parse does it, do does it, any, all. Because people aren't generally probably trying this. You're probably not saying, oh, code, put it in a variable and then running an all and passing it the code where somewhere in the middle of it you're changing the code. But there were a lot of places where if you did that, you could crash it. People just weren't doing it. Yeah, as I say, it sounds like it might be limiting, but since you're only locking enumerated series, you can usually find a workaround. So you could just put a group inside of a block that lives at a fixed position, and then you can add code into that. The code outside of the group can add code inside of the group. So you have kind of a workaround. Similar things for parse. This was kind of there's a lot of cases in which throws would get missed because throws were sort of part of a return convention, a special kind of value. Ren-C doesn't do that. There is no value for a throw. It comes back as a Boolean out of every thing that can throw. So anything that can throw ends in the name throws, which helps you read it out loud and not forget to check the Boolean, because you're reminded because it's in the name and it reads pretty well. Many cases of that were fixed. R3 alpha didn't really have a debug build. There wasn't some set of systemic asserts. There were some asserts, but they weren't really debug build asserts. They were just, they would do what I would call a panic. So they were in the release build, anything that said assert. And Ren-C has gone through with, address sanitizer, valgrind, run it all the time. And Shizhen came up with a pretty smart workaround for certain kinds of problems where we just don't use pooled memory. We just always allocate memory through malloc, which is going to be slower, but at least that way you're getting the address sanitization properties of malloc that's been hooked instead of running up against that. So that's poor man's version of implementing address sanitization on our pools. And Yeah, we try to pass all the tests, except for one that's not passing today. But I don't really understand the philosophy that drove the concept of test diffing, but Andreas and Ladislav were pretty interested in this concept of having a test suite that you accept that some of the tests are going to fail, and then you diff it, and on some platforms you know what to expect, and you kind of keep your state. I prefer to put a test in the bug tracker until you've fixed it, at which point you add it to the test and they all pass. And that's I think, been better for reliability. In Stack Overflow, they're very, they don't like it when people ask a question about how do I do this in C/C++? And they're like, there is no such language as C/C++. But I hate to break it to them. I've been programming in C/C++ for quite a while now, because Ren-C is using certain aspects of C++11 to do some good static analysis while still fundamentally not requiring a C++ compiler. So if you're not running those if-def branches, the code looks the same at the call sites. It's still the same C code. It's just that you're getting more checks if you are using the C++11 build. And something I just point out that Carl had written, which was that it, is highly tuned code should only be modified by experts who fully understand its design. And so one of the big pushes that I've tried to do with all of the work is to put more self-checking into it, so that there's a debug build. So it should, all this stuff sounds really fiddly and it might sound really hard to get right, but I think it's actually a lot more self-healing code base, having the debug build and going through address sanitization. We've done some other static analysis. So this is a pretty important problem, which is the specificity of binding. The way that R3 alpha would resolve a word in a recursive function would be to look for the most recent instance of that function on the stack. That might seem logical, but not really, because binding is pretty important in Rebol, and especially when you're picking up generic code and you have something that's like a while loop, and then you put another while loop inside it, but it's using words and their bindings have meaning at each recursion that it doesn't want to lose just because it recursed. And you might say, oh, well, you're writing the recursion. Can't you just work around it? Well, no, not if it's a user who is doing that composition not knowing how you've implemented it. They are combining parts in ways you may not have predicted. And so specificity of binding is pretty important. So this recursive function, you would think that it should have two distinct notions of x. And the only way you could get this in R3 alpha was basically to make an object that represented the parameters for the function, and then copy the body and bind the copy of the body to that object, and then run it. And some of you would know or not know that that's what closure was. That's pretty expensive to have to do that each time you call the function. So what Ren-C does, it fixes the problem at a reasonable cost. The mechanics of it are a little bit beyond the scope of this talk, but it is not necessary to make a copy of the function body and rebind it, because what happens is that the body remembers what it's bound relative to, and through the stack, through the execution stack, something called a specifier is used to point out a frame, and each function call has its own unique frame, so that when this block goes down here, you might have remembered that I said cells are 4 platform pointers, and that an SRI, a series, and an index, that's 2 more platform pointer size things. Well, Ren-C uses that last fourth pointer in the extra field for blocks to when this value is executing, when the body executes, that a unique identification of this frame, which may be a series like an object, or it may just be the C function pointer, it depends, based on what's called reification. So that platform pointer gets reunited with the appropriate relative values at each stack level. So it's threading through a stack-based property that travels with the value each time that value is evaluated. You don't have to really understand all that or follow it right now. All you have to know is that in this case, no copy of this body needed to be made or rebound. It is one body that is still able to get the right answer for knowing that the x from the first level of recursion, where it was 2, is different from this x as well. So you get that benefit that used to take a closure, that used to require making a copy without a copy. So yeah, here I am talking more about it. And I really do believe that when you start looking at these things, you know, sophisticated users like Ladislav, sophisticated users who were trying to do things that were complicated, came across the need and realized they needed a closure for that reason, as well as sometimes, you know, the other reason would be capturing variables so they would outlive the function frame. And JavaScript can do that. You know, if you declare a function inside of a function and the inner function refers to a variable that's in the outer function, and then you pass the inner function back or something, it will capture the variable even though the outer function's execution has ended. And I don't think we should give JavaScript that like victory point. So still looking at how to do that particular feature, which again, we can do it now only keeping the arguments alive. We don't have to keep a rebound body to those arguments alive. But that's still more cost than I'd like. So I'd really like to find a way that we can more granularly only pay for the creation of the indefinite lifetime variable if there's a move that moves a cell outside of the function call. And we do have mechanics to try doing that. That particular thing has not been done yet. I talk about this stuff, and it is trickier. The code has gotten trickier, but I think it's manageable. And something that helps make it manageable is that the C++ build is able, for instance, to distinguish a value that has been reunited with its specifier. So rebval is a known, fully specified value. And a relval is it's like one of those values inside that function body that hasn't been reunited with a piece of frame information that comes through the stack to tell it which recursion it belongs to. So some things you can do, like molding, you can mold out a value without knowing what it's bound to. You can print it. The only time you need to get values fully resolved is if you're going to look up if it's a word and you want to look up what the value of that word in the context is. So some parts of the code deal in relvals, which may or may not be fully specified, and it has to be unified. This transition turned out to be easier than I had expected. There weren't as many problems, and certainly having the C++ static analysis benefits and the data typing that has helped that a lot. So there's a long-standing problem that was known about in R3 Alpha and Rebol 2, which is that return was just a native, like anything, and so that meant that there's only one return, and again, its only way of deciding what to return from was to climb the stack and to say, well, what's the last function that was called? And you say, well, how could that be? Because you could say if something, and then inside the block return, why wouldn't it return from the if? Why is it returning from the function containing the if? It must have worked. Well, no, it just had kind of a simple rule. The simple rule was, if it's a native, then don't consider it a candidate for return, because it couldn't be. But what that meant is you had this barrier, like imagine you're writing your own version of if, like this one. And this has the behavior of doing what you would think. The body, we're doing the body here, and it doesn't know what to return from. You meant return from test. You didn't mean return from my if. But because my if was not a native, it didn't get the exception that enabled the behavior. So Ren-C has definitional returns. And the concept behind definitional returns is that return is a local variable that the func generator or function generator creates that is itself a function that knows which function to return from. And as a consequence, you end up being able to, in user mode, write your own loop constructs, write your own ifs, things that will now work properly with return, which is important. And you might say, wait a minute, if it's a function, well, it's a function that wasn't created with a generator that has a local return. So return is created using a more foundational function generator, and then func and function are higher level function generators that do give the generated function a definitional return. So it's just a local word that is bound like another local variable in the function would be. And typo. So yeah, as I say, the function generators are what creates it. You can write your own user mode function construct that does what I just said, and it does work. It's 4 times slower or so than the native one, because the native one uses trickery. I'm not that concerned about the fact that there's a performance difference as I would be just if people couldn't do it. You know, if you as a user writing your own function generator couldn't do the same trick, I'd be more bothered than I am by the fact that you can't do it as fast as the hand implemented func and function generators or function generators do. So I've already in another demo kind of gone over one of the real key points of R3 Alpha's implementation that has been taken on and continued in Ren-C, which is that it really is more or less ANSI C89 with a few exceptions. And this was true in R3 Alpha as well. Carl would sometimes use the / style comments. And even though many C compilers have supported those, you know, between 1989 and 1999, technically speaking, they're not in the standard. But if you wanted to, you could build it just by stripping all the comments out, and you'll be able to build it. So it's not that big a deal. And R3 Alpha wanted to standardize the size of integers and wanted to standardize it to 64-bit. And so it used this feature that only became part of the C99 standard, and that was the long longs. I don't think that that's the way that I see it. I think that arbitrary precision integers are important, and I think we can finesse things in such a way that we don't have to use long, and that we can still do some tricks so that you use your native integers if you don't have to expand it out for the purposes of that arbitrary precision number. We use the inline keyword, but every usage is inline static, so you could just pound define inline to nothing, and it would just become a static function, which would still compile. And there's initialization of declarations in the middle of a function, which typical historical C practice, you would put your declarations at the top, and then you would initialize them later. But I really don't like doing that. So we could transform it. But the main point being that, yeah, we're building on this very old, stable, well-studied foundation of C. And I really do believe that modify with confidence, that used to be my motto for what the goal was, that I was going to build a core and hopefully hand it off maybe to Atronics or something. Just say that, if you have an experiment, if you have an idea you want to try, that the system is resilient enough that you can do that. So I think we got to that point a year and a half ago or something. I think that the modify with confidence has been demonstrated repeatedly because the modifications are happening with confidence and features are coming online and they are working. So I've been changing the motto. I announced that at the beginning of the year, that last year's theme was elevating the art. So the art of Rebol has been going forward. So I hope I've covered, this is supposed to be just a good overview of the technical points that can be understood by others implementing Rebol-like systems, or by Carl if he wants to know what's happened.